Yeah, thanks, Natalia, and good afternoon, everyone. And I will start sharing my screen. I hope you can easily see.
Yes, we can.
So great. So today, as Natalia mentioned, what I would like to do is just give you a brief overview of the infrastructure that we offered within the VIPERLAB project. As mentioned, is about sheet-to-sheet, let's say, processing for the perovskite technology. And I will give you also some, let's say, example what we also achieved using the infrastructure that we can offer. So maybe to start with, for the people who are not familiar with TNO, so TNO is the Netherlands Organization for Applied Scientific Research. So it's a no-profit, let's say, company, and let's say that the main purpose is just to develop knowledge and innovation that for the well-being of the society. So as you can see from the pie chart on the bottom part, actually the TNO works on very different topics from let's say the one that we're working, so the energy material transition, to defense, mobility, strategy, and so on. So specifically for the energy and material transition is the one where let's say the unit where I'm working personally, and is, let's say, of course, focusing on the, let's say, innovation for the energy transition in our society. We have different locations, as you can see from the map. Specifically, the work in solar is done in Eindhoven here and in Petten in the north. And let's say the facilities that we offer within this project actually located in Eindhoven for the perovskite technology. So we are located in what we call a high-tech campus, or what you see here on the left. So it's a lot of companies, high-tech, and yeah, within these companies also us. We're located in these buildings, and as I mentioned, most of the facilities that we offer here are located here. But we have also several facilities for, let's say, module integration and silicon in our other location in Petten, if you're interested. So let me start also say something. So we usually have sometimes people confuse us with Solliance. So officially we are TNO, that we are partnering in Solliance, and say Solliance is an alliance, let's say, between different research institutes that you can see here. So there is us indeed, IMEC, ULIC, and different universities, technical university in the Netherlands, so Eindhoven University and Delft University, Twente and Groningen, and the University of Hasselt. And let's say within this alliance, actually, we collaborate a lot with different industrial partners. So this is just a kind of sketch of companies we work with in the past and currently. And you can see that we span through all the different value chain, from materials, equipment, PV producer, and end users. Okay. So let's say after this brief introduction, I will move towards, let's say, the infrastructure that we would like to offer, and we offer within this project. So as I mentioned at the introduction, we talk about scalable process routes. So I will go through, let's say, several, let's say, options that we have. So from the solution process to ALD, sputtering, laser, and encapsulation. So the main purpose of anyhow also our work is just to, let's say, move, let's say, the perovskite concept from a small area. So let's say something that, let's say, most of the people work at university can relate with. So very small devices, to something that is, let's say, in the range of 100 square centimeter, using all these type of different technique that are much more industrial relevant. And the idea just to have a proof of concept at what we call intermediate area. So we are not actually a producer, so we're not going to make a full devices, but I think we can screen a lot of different things applying this technique that can be really used in an industrial environment. And of course, our aim is also not just to look at only the efficiency, but kind of combination and trade-off between, I think, these 5 pillars that are on the top left. So efficiency, but of course, stability of the device, the scalability, the cost, and of course also the sustainability of the solution that we want to implement. So one of the let's say the technique that we use a lot is slot die. So we we want to deposit most of the layers for the perovskite technology by solution process, and we believe that slow dye is definitely a lot of advantages and benefits. So it's compatible with sheet-to-sheet and roll-to-roll manufacturing process, for instance, and allows, let's say, the very simple patterning like stripes and squares. And we can do the deposition of different transport layers, and of course deposition of different perovskite formulation and band gaps. And we currently do, let's say, deposition and coating, coupling, let's say, the slow dye with a vacuum quenching process, let's say, to have a uniform perovskite absorber. Coming up, actually, we're going to start to work with a gas quenching process. So this is also something that we will offer in the next year. And at the same time, also we look at incompatibility with ambient processing. So, and this is both for the sheet-to-sheet, also for the roll-to-roll, but yeah, the roll-to-roll is not part of the VIPERLAB infrastructure that we offer. But if you're interested, I think you can always contact us. So in terms of infrastructure, I think we have different slow dyes machine that we use. So I think well, the first one on the left is the one that we mostly use for our baseline. So it's a slow dye within a glove box. So we can use, let's say, an ST solvent system like DMF. And let's say to up to an area of more or less 6 inch. And yeah, we always couple, as I mentioned, with a vacuum quenching chamber. So in the middle, you see another slow dye. This is, let's say, can cover an area of 30 by 40 centimeter, and we can do the coating in air, so in the ambient atmosphere. And again, we combine with a vacuum quenching chamber. This is more automatized line, so there is a robot that pick up the glass and transfer to the different, let's say, furnaces and so on. And as I mentioned before, I think they're not really in VIPERLAB, but we also have, let's say, slow dye couple in a, let's say, roll-to-roll line for, let's say, roll-to-roll processing, again, in ambient. So, and let's say the last two solutions, for instance, we cannot really use nasty solvents. So we try to develop, let's say, more green solutions, green solvent solution formulation and so on. And just to give you an example, I think especially with the first infrastructure, the one where we use the slow dye in the globe box, actually our baseline is a semi-transparent stack that you see here. So we always complete with an LD layer and a sputtering layer on top. And let's say, yeah, essentially what we observe and what we see is that when we move from a lab scale to, let's say, a little bit, let's say, more large coding and then cutting down as making still small devices, let's say we can still get very nice performance. So in the range of 20%. So next to that, let's say for the solution process part of the something that we do a lot, and we have a lot of experience is ALD technique, and specifically spatial ALD. So is atmospheric pressure spatial ALD, and let's say we use it to deposit this metal oxide layer that can be relevant for the perovskite architecture. So of course we go from, let's say, the tin dioxide that is I think the baseline, but we can also deposit, and we have knowledge how to deposit different type of N-type layer and dielectric layer that can be relevant according to, let's say, the user. And we have two actually reactor at the moment that we can use. So the first one is the one what we call a lab scale reactor. Is a rotary reactor where we can do like very small samples in the range of 3 centimeter by 3 centimeter. And then we are upscaling, let's say, some process also on a larger tool, so that can accommodate a 6-inch substrate. And actually, this let's say that the reactor is inside a globe box, so it's I think can be used also, for instance, for perovskite initiative. And let's say in terms of also here, I would like just to give a sketch. So let's say since long time ago, I think we demonstrated that let's say the layer that we deposit is very beneficial for the long-term stability of the device. And yeah, we demonstrated a single junction device that is thermally stable, light stable. And let's say the same layer that we deposit, for instance, we use to make multi-junction perovskite devices in collaboration with our partner at the university. So both to make tandem, and I think in the past also we did one of the first triple junction perovskite device with this, let's say, using this layer. Then I will move to the sputtering process. I think we have different sputtering machine that we can offer. So linear tool and rotary tool, DC and RF source. And I think one of our main goal is just, for instance, to improve the quality of these TCOs, especially for the near-infrared transmittance for tandem application. So we spend a lot of time to optimize, for instance, ITO and IOH. And I think what you see in the graph are just example how, for instance, the transmittance in the infrared for our stack is, I think, like one of the top notch. I think more than 90% all over the infrared spectrum between 800 and 1200. Especially if you compare, for instance, the blue with let's say the green, the gray, sorry. And I think we apply the same concept of the IOH to see the benefit in a perovskite tandem architecture. Again, this is in collaboration with our partner at the university. And you see, for instance, the response in the infrared for the subcell, the bottom subcell of the perovskite, that is enhanced when we use, for instance, this specific TCO that we optimize. Next to that, I think we have several infrastructure for laser processing. I think we have several setups that are, let's say, in the picture on the right. So some of them are in ambient, and some of them are, and I think one of them is in a globe box. And the one in the globe box, for instance, we use for, let's say, specific, let's say, task on the perovskite for a safety reason, of course. And here, let's say in this slide, there is a sketch of what we typically offer. So we can typically work for the conventional P1, P2, and P3 monolithic scribe connection. And yeah, you see basically an example in the, let's say, in this picture. But I think also we're working a lot with backend processing. Where, let's say, yeah, so you have the full stack, the semi-fabricate, and then let's say you do the scribe, use the different things. And I think this is, I think it's interesting if you, of course, you want to do something a little bit more unconventional than the classical, let's say, very rectangular shape devices. And this is an example of, let's say, a perovskite backended with hexagonal shape. And then finally, also we look at how, let's say, we do translucent device. So I think with the laser we ablate, let's say, part of the stack that we deposited. And here there is an example that from, for instance, on a flexible foil is a module that we fabricated in the past, and then we ablate to make it like this kind of translucent, for instance, for Windows application. And we have different, let's say, wavelength for the laser. I think the one more important for this type of work, different, let's say, pulse regime. And I think the area I wrote 30 by 30, but this is mostly for the, let's say, let's say the setup in the globe box. This is the maximum size that we can accommodate there. And the other, I think, platforms, I think, accommodate even bigger plates and substrates. Also, we have a lot of experience that we can offer, let's say, different encapsulation methods. And of course, we can also take a look at the stability of these devices. So this is just a very kind of glimpse and let's say what we can offer in terms of encapsulation. So I think we developed method for what we call 3-glass encapsulation, a 2-glass glass. We can apply flexible barrier foil on, let's say, the glass. We also experience to do what we call direct encapsulation, where we have a thin film structure on top of the real device. And of course, because we work also a lot with, let's say, flexible devices, we develop, let's say, the encapsulation procedure for having a fully flexible device. And we are currently looking at how to do the direct encapsulation, for instance, on a flexible device. And yeah, so with this one, I would like to move towards a few examples of what we achieved using this type of infrastructure. So let's say, so I'll give you just, as I say, a few examples. So with let's say, most of the machine that we use, I think we can produce, let's say, rigid perovskite modules, again, semi-transparent with, let's say, an aperture of 10 by 10. So it's an aperture of 100 square centimeter. with a really high geometrical fill factor and high bifaciality factor, so above 90%, with efficiency in the range of 16%. And we can use the same process, let's say, using instead of a glass substrate as an initial substrate, but with a foil, so it's a PET coated with ITO. And yeah, we can. We think we got efficiency in the range of 13%. I think same aperture area, same geometrical fill factor, bifaciality is a little bit higher because efficiency is a little bit different. But yeah, I think we essentially have a procedure to use both type of substrates. And in terms of the reliability, we have different climate chamber, and say for the dump pit test, we have light soakers, we have climate chamber with light soaker integrated, and we can do a lot of thermal cycling. And I think, yeah, with all these techniques, for instance, in the past, we demonstrated, let's say, the capability of, let's say, the large area device that we fabricated that can pass, for instance, light soaking test for 1,000 hours at maximum power point, and several tests of the IC, so dump pit, and for instance, thermal cycling with not so much of loss. And of course, we spend also a lot of time to make, let's say, tandem architecture. So this is a few example of, let's say, the module that actually I presented before that we combine with an area match measurement, for instance, with silicon or for instance with CIGS. And I think, yeah, we get very top-notch results. And so I think the range of 25%, more than 25% for terminal tandem with silicon, and almost 22 with a CIGS on relatively, let's say, large area, 100 square centimeter and 85 square centimeter. And of course, yeah, I think this is just example of 40, but we work also on different substrates directly to make two-terminal architecture, both on silicon and CIGS, if you're interested for the next call. And yeah, with this one, I think it brings me to the conclusion. And yeah, I would like to thank all my colleagues that work, of course, here. And yeah, and they can, let's say, help you if you're interested in a joint experiment. Thank you for your attention. Thanks.
Okay, thank you very much. Let me check once again. So to everyone, if you have any questions, please write them in the chat, and then we will read them to the